Welcome back. In this video, we'll continue right where we left off in part 1. We'll focus on 3 key goals. First, we'll enable the DEX to handle requests from liquidity providers. Second, we'll introduce the Liquidity Provider agent to simulate adding and removing liquidity. Third, we'll explore blocks in HoloBit, a powerful feature for packaging well-built components into reusable building blocks for future projects. Before we start, let's review a basic concept. Adding liquidity simply means a provider deposits 2 tokens into the pool. To keep the price stable, these deposits must match the pool's current reserve ratio. In return, the LP receives LP tokens, which represent their share of the pool. Removing liquidity is the reverse process. The provider returns their LP tokens to the pool to reclaim their proportional share of the underlying assets. For the adding liquidity scenario, we have 2 agents, the DEX and the liquidity provider. Imagine an LP wants to add ETH and USDC to the pool. When the DEX receives this request, it needs to check the current reserves of these 2 tokens, calculate how many LP tokens to mint, deposit the user's assets, and send the new LP tokens to the user's wallet. Let's upgrade the DEX first. We need one new variable, totalSupply. This tracks the total LP tokens in circulation. We also need 3 new processes. CalQuote, a process that calculates the required amount of a second token based on the first. CalcLiquidity, a crucial process that calculates exactly how many LP tokens to mint based on the deposit. addLiquidity, the core process that executes the transfer of assets. Next, for the liquidity provider agent. Much like our trader agent, the LP needs a wallet and a defined behavior. We will create a container for the wallet. It holds the 2 trading the tokens and the LP tokens. Create a process to send the addLiquidity request. With this blueprint, we have the basic structure for both our DEX and liquidity provider. Now let's make it functional. We'll start by configuring the DEX. Our first step is to refine the LiquPool configuration so it can recognize LP tokens. Go to the Property panel of LiquPool. In the Batch Keys field, enter the following expression. Here, we use a construction helper called productJoin to take the ERC20 tag set and lists all pairwise combinations of its tags, like ETH-USDC. Next, open the DEX individual property settings. Under LiquPool, add 2 rows for the LP tokens of these 2 trading pairs. Set their initial amounts to 0. Since the LP tokens are sent immediately to the user after minting, the pool's holding balance for these tokens remains 0. Then add totalSupply to the table. For an existing pool, its initial value is the square root of the product of the pool's reserves. Set this value based on your specific trading pairs. Now let's build the logic. We'll start with CalQuote. It calculates how much token B is needed for any given amount A, ensuring that any new liquidity preserves the pool's price ratio. First, let's define its ports. CalQuote needs 3 input ports, amount A, the LP's input amount for token A, the first token in the pool, token B, the second token in the pool, and 1 output port, amount B, the required amount of token B. Remember to set the type of token A and token B to string. Second, let's build the process. Inside the process, add a compute component followed by an end event. We'll use the default passive mode for the start event. In the compute component, enter the formula to solve for amount B based on the ratio of the existing reserves. And with that, CalQuote is ready. Next up is CalcLiquidity, the process that determines how many LP tokens a user receives. First, define the ports. For the inputs, we add 4, amount A, amount B, token A, token B. For the output, we add 1, liquidity, the number of LP tokens to mint. Again, remember to set token A and token B type to string. Then, we build its logic. The logic here is critical because the DEX must handle 2 distinct cases. If total supply is 0, it's a new pool. Liquidity equals the square root of the amounts. If total supply is not 0, the pool exists. We calculate the proportional share for both tokens and take the minimum value. So we need a gateway to branch on the condition, and on each branch we add a compute component to calculate liquidity. Then merge both branches into a single end event. Let's configure it. Use the default passive start event. For the gateway, set its type to conditional. Add the condition if total supply is 0. If true, follow the create pool branch. Otherwise, follow the addLiq branch. On the create pool branch, the formula will calculate liquidity as the square root of the product of the two deposit amounts. On the addLiq branch, the formula will calculate the proportional share for both tokens and take the minimum of the two results. You might ask, why take the minimum? This is a crucial safety mechanism. If a user provides slightly unbalanced assets, we only credit them for the smaller, limiting amount. This protects the pool's price ratio from being skewed. Now, our calc liquidity process can accurately compute liquidity for any situation. Finally, let's build addLiquidity, the process that executes the actual liquidity provision. Start with the ports. When an LP sends a request, the DEX needs 5 input ports: token A and token B, set type to string. Amount A and amount B, LP wallet, a container port for the LP's wallet, and 1 output port of liquidity, the number of LP tokens the LP will receive. You'll notice similar ports across processes. This is a deliberate choice. Breaking the logic into modular steps makes the model far easier to understand and debug. You can certainly explore ways to consolidate these, but for now, clarity is our priority. Now define the behavior. First, we'll use a call component to call the calc liquidity process and determine the correct amount of LP tokens. Second, a container operate component will handle the complex asset movement, transferring tokens from the user's wallet to the pool and sending the new LP tokens back to the user. Finally, add an end event to close the process. Let's configure them. Use the default passive start event. For the call, set the owner to self and choose the calc liquidity behavior. Then, wire the input ports accordingly. In the compute after action formula, assign the result to the liquidity output port using liquidity equals this dot liquidity. Now we configure the container operate component. First, update the pool record of LP tokens. In the compute before action formula, enter this expression. This dynamically constructs the LP token name and adds the newly calculated liquidity to the record. Next, let's set up the token flows. Drag LickPool and the LP wallet container port into the process to create their references first. We have 2 flows, one for input tokens. Token A and token B flow out of the LP's wallet, through the container operate, and into LickPool. Another for the LP tokens. The new LP tokens flow out of LickPool through the container operate component and into the LP's wallet. Enable exchange mode and configure these flows with the correct token names and amounts. For the input tokens flow, from LP wallet to container operate, add 2 operations. Set the container keys to token A and token B, and the amounts to amount A and amount B. From container operate to LiquidPool, use the same keys and auto amount. Then for the LP token flow. From LiquidPool to container operate, use the join expression to set the key and the amount to liquidity. From container operate back to LP wallet, use the same key and auto amount. This ensures the user's tokens are deposited, and the newly minted LP tokens are sent back. Finally, we update the DEX's overall statistics. In the compute after action, add the logic to update total supply. And with that, the addLiquidity behavior is complete. Your DEX is now ready for liquidity providers. Now let's shift our focus to the liquidity provider agent. First, let's configure its basic properties. Set its type to population with an initial size of 3. Next, the LP wallet. Use the same ERC20 tag set for the keys and append the product join expression to generate the LP token names. We'll leave the capacity infinite, set initial amount to 0, and allow negative balances. With the wallet ready, let's define the behavior, goAddLiquidity. This is an active process. The flow is straightforward. After the start event, the agent will find a trading pair to interact with. It then uses two call components to communicate with that pair, and finally reaches the end event. Let's configure the details. Set the start event to timer. Enable active. Let's schedule it to add liquidity for the first time at tick 21, repeating every 10 ticks. For the find component, set its scope to dex.all. In the advanced settings, add a pre-filter with the condition. This tells the agent to find any pair whose name contains ETH. Since there is currently only one ETH pair, this effectively targets our specific pool. You can also use a strict equality check, just as we did before. Now for the two call components. The first call is a query. Set its owner to the find pair result and choose the calc quote behavior. For the inputs, we'll use amount A 100, token A, ETH, and token B, USDC. The second call is the action. Set the owner to find pair, but this time choose the addLiquidity behavior. Then pass in the same token names and amount A. For amount B, we'll use an expression to read the result directly from our first call. Finally, for the LP wallet port, simply drag the LP's own wallet into the process to create a reference and connect it. And just like that, the LP's behavior for adding liquidity is fully wired. Before we run the model, let's add a useful feature for testing, control switches. This will allow us to easily enable or disable the trader and LP agents. For the LP, create a new variable called LP active. Then add a controller for it, setting its type to a Boolean switch. Now, back in the goAddLiquidity process, insert a gateway right after the start event. We'll configure this gateway to check our new switch. If LP active is true, the process continues to the find component. If false, it branches directly to the end event. We'll apply the exact same pattern to our trader agent, creating a trader active switch. This modular control gives us a clean way to isolate and observe each agent's impact on the system. Now let's run a small test. First, turn on the LP active switch and turn off the trader active switch. Run the model and observe the liquidity pool. At tick 21, you should see a sharp increase in the pool's reserves, a clear sign that the process for adding liquidity is working perfectly. Then you can turn on the trader active switch and see the price trend changes as traders buy or sell. If you need to deep dive into the model's calculation, HoloBit's debugging tools are very helpful. For example, in the addLiquidity process, you can right-click the Container Operate component and set a debug breakpoint. The model will pause automatically when it reaches this point. Here, you can inspect critical intermediate results under the Call Stack tab in the console. The top section shows the execution path, the chain of calls that led to this exact moment. The bottom section gives you a snapshot of all local variables and port values. You can verify the output of calc liquidity, check the wallet balances, and confirm every detail before the transaction completes. Once you're done, simply remove or disable the breakpoint to continue. So far, we've only covered adding liquidity. Let's briefly discuss the logic for removing liquidity. The process is very similar, so we'll highlight the key differences. On the DEX side, when an LP removes liquidity, they return their LP tokens. These tokens aren't stored, they are burned or destroyed. So we'll need a new container to temporarily hold these returned tokens before they are burned. The behavior logic remains calculate first, then act. First, you'll create a calc withdrawals process. Its job is to take an amount of LP tokens as input and calculate the corresponding amounts of the two underlying tokens to be returned. Ensure its input and output ports are configured correctly for this task. Next, you'll build the removeLiquidity process. It will first call calc withdrawals to get the return amounts. Then it will use a container operate component to execute the asset transfer. Here, you'll need to be precise with the connector settings. Pay close attention to the direction of the transfer, the token keys, and the amounts. Finally, it must decrease the total supply by the amount of burned liquidity. On the LP side, the goRemoveLiquidity behavior is also an active process. To model this as a single event at tick 71, we'll use a neat trick. Set the timer to trigger once per tick, but set the total times to 1. This ensures it runs at its first opportunity and then stops. Inside this process, configure the find component to look for the USDC and WBTC pair. Then call its removeLiquidity behavior, like requesting to remove 10,000 units of liquidity. With this implemented, go back to the root canvas and run the model. You should observe a significant drop in the liquidity for the USDC and WBTC pool, confirming that our removal logic is working as expected. Now everything works. Let's do a bit of cleanup. Adjust the layout to make it more user-friendly and intuitive. At this point, our agents are complete. We've not only built a functional AMM model with swapping, adding, and removing liquidity, but we've also established a powerful, reusable pattern for simulating DeFi protocols in HoloBit. By using expressions and modular design, we've created a model that is robust, easy to debug, and ready to be extended with more features in the future. Now, this powerful model is ready to be shared. You can publish it to the HoloBit marketplace, allowing the community to download it, inspect every detail, and even build upon your work for their own projects. That's the collaborative spirit that drives innovation. Now, let's go one step further and look at how HoloBit's block features can turn our work into reusable assets. A block is essentially a user-defined component. You can take any complete unit on a canvas, like a process, an agent, or our DEX agent, and save it as a block. Let's turn our DEX agent into a block as an example. Right-click the DEX agent. Choose blockrize and confirm. Your new DEX block is now stored in the workspace. You can find it in the left sidebar under the Block tab. If you need to make changes later, hover over the block in the list and choose the Edit option. This opens a special edit mode. When finished, click Close Edit to exit. Now, let's create a new model scenario to show how to use it. Here, we'll simulate a pool of ETH and DAI on Uniswap version 2. Simply drag the block onto the canvas, just like a built-in component. Then configure its type on the property panel and the variables in the property settings. Quick settings, right? Blocks solve the problem of direct reuse. You can drag and drop them into any project, saving you from rebuilding the same logic twice. But what if you want a pro version of a block with slight modifications? For example, a Uniswap Pro. It's just like our standard DEX, but with an added protocol fee. Instead of copying and pasting, we use inheritance. Inheritance means the new agent possesses all the properties and behaviors of the original, while allowing you to add new ones. Let's build it. Create a new agent and name it Uniswap Pro. Enter its canvas. From the Block tab, drag your existing DEX block onto this canvas. By doing this, Uniswap Pro automatically inherits everything inside the DEX block. We can expand the block instance to see the internals or collapse it to keep things clean. Now, let's add 3 new elements on top. A fee switch variable with a controller, defaulting to on. A protocol fee ratio variable, set its value to 1 divided by 6. A V2 container to collect the earnings, set its keys to the ERC20 tag set. Then set its type to population and configure the trading pair, just like we did for the standard version. Later, we can see the differences in their performance. Next, the logic. We need to hook into the original swap process to charge a fee. Here we take the swap-in scenario as an example. Create a new process named swap-in and calc protocol fee. The ports should match the original swap process exactly. Inputs: amount in, token A and token B as strings, and trader wallet as a container port. Output: amount out. Inside this process, we build the extension logic. Insert a call component, a gateway, a container operate, and an end event. First, the call component. Set it to call the original swap-in behavior. This reuses the core logic so we don't have to rewrite it. But remember to pass data to the input ports correctly and assign the result to the output port. Second, the gateway. Set its type to condition. Check if fee switch is true. If true, go to the container operate component. If the switch is off, the process simply ends. Third, the container operate component. Drag the inherited liq pool and the new fee to container into this process. Connect the flow from liq pool into the container operate, and then into fee2. Ensure exchange mode is switched on. For the outgoing flow, set the key to ETH. For the amount, enter the formula to calculate the collected fee. For the incoming flow into fee2, use the same key and set amount to auto. This is the power of inheritance. We built a pro version with fee logic without touching the original stable DEX mechanisms. Now to verify our work, let's introduce two trader agents into the scenario. One for the standard DEX and one for the pro version. Simply copy them from our previous scenario to save time, but be careful. Direct copying requires specific adaptations. Here is your checklist. First, clean up the logic. Since we are only testing the fee mechanism with swap-in, we should remove the swap-out process. This keeps the test clean and prevents potential errors from unconnected ports. Second, and most importantly, update the call targets. For the standard trader, ensure it points to the first individual of Uniswap version 2 and calls the standard swap-in behavior. Also, remember to wire up the input ports. Back on the root canvas, let's do some layout adjustments to make the connections easier to follow. For the new Trader Pro, copy and paste the trader. But this time, you must retarget the call component to the Uniswap Pro agent, the first individual, and switch the behavior to the new process we just created. Once the connections are updated and verified, go back to the root canvas. Here, expose the new properties on the agent node and adjust the layout for clarity. When you are ready, run the model. You can create charts for liq pool and fee2. Observe the data changes. You should see the fees accumulating in the new container. Notice that the ETH in the Pro pool plus the collected fees roughly equals the total ETH in the standard pool. This confirms our settings are correct. Just like this, you can use this pattern to create endless variations, different fee models, curves, or incentives, and test them instantly. Finally, let's touch on the marketplace. Once your block is ready, you can publish it. Go to the Workspace library. Under the Block tab, right-click your agent block and choose Publish to Marketplace. Fill in the information, including the cover image, the test file, tags, and description, and confirm. Then go to the Marketplace and select the Recent tab. You will find the block you just published. Here, you can download blocks from other creators or share your own. It allows us to build upon the community's collective wisdom, turning individual models into a library of powerful, shared building blocks. That's all for our second video. Let's wrap up by looking at the bigger picture. Across this two-part series, we've achieved something significant. We started with a simple mathematical formula, x times y equals k, and evolved it into a living, breathing DeFi ecosystem. In Part 1, we built the engine, the core swap logic, and the market mechanics. In Part 2, we added the fuel, the liquidity providers that make the system dynamic. But, most importantly, we learned how to scale through blocks. This is the true power of HoloBit. It takes us from building in isolation to modeling together. By publishing to the marketplace, you fuel a global library of building blocks. So, go beyond Uniswap. Use this blueprint to design and simulate the next generation of protocols. Thanks for watching, and see you in the next episode.